Hi, Robin here. Going to look at thinking logically. This is part of component 2 for the OCR A-Level Computer Science. Thinking logically is where we really need to start thinking like a computer does. So as you can see there, an algorithm runs on a computer, therefore we should follow the logic of a computer. And ultimately, a computer uses electricity is either there or it's not, and therefore we have a true or a false state, and therefore we use that to our advantage. And obviously we use things like 0 and 1s in our calculations to represent data, etc. So in other words, what we're trying to do is, by thinking in the same way as the computer, we are therefore able to work out sort of algorithms and logic and processes that will actually work on the computer itself. So again, another feature of a computer, which is obviously there, is the electrical circuit itself. And obviously we have different logic gates that work with this. Simple example, we've got an AND and an OR gate. And again, if we think about the usage of these two, so with an AND gate, for example, we've got two inputs going in. If both of those are on, then we get an output. So obviously if that's an alarm is set and the sensor is triggered, then the alarm will send a siren, and therefore we've used the electrical circuit to carry out the logic that we needed. Another simple example, we've got an OR gate here. So if there are chips, I can have a meal, it'll go through and pass. If there is a pie, I can have a meal. And if both are present, well, I suppose I have a really good meal. And then again, that gate is allowing that process to happen. So we can use these, and obviously combinations of these, to give us much more complex algorithms, but we're using the processes of the computer to achieve that. Other examples obviously would be like a NOT, giving us the opposite, or an XOR. And obviously we can combine the logic of these and sort of how we think about them to really, like I say, create really complex algorithms. Again, following on from that, we can obviously use mathematical logic as well, and therefore we can obviously perform things like arithmetic. We can make comparisons, therefore. So in other words, we can create controls, particularly to things like loops and other mechanisms where we can say this is greater than, and that causes that change to happen, or it now equals the same as, and therefore we're now going to stop some way. Ultimately, what we're wanting to be able to do in algorithms and processes have decision points. So like I've just had with the mathematical things, we can now do that with other processes as well. And ultimately what code allows us to do is carry out selection and branching. The two terms, we need to apply them appropriately, but giving us that opportunity to ask an if question. If this is the case, I'll do this, and if not, I'll do that instead. And again, what we're trying to do is constantly, by reminding ourselves of these things, and I can understand if this seems obvious at first, but by reminding ourselves of this, it helps us to think in the way the computer's thinking, and therefore we can write appropriate algorithms. Again, by having the ability to have an if statement that moves somewhere else in code, we therefore have the ability to repeat code, and that gives us the ability to have loops, for loops, while loops, for example. We can control what happens with that. And again, when we're writing an algorithm, if we think to ourselves, okay, well, actually, I want to repeat what I've just done, that same process. Well, actually, what kind of loop do I need to use? What's appropriate for that situation? Things that's really important when we think about algorithms is to think about the complexity and the big O notation. A separate video on this, which I'll put a link onto, but that will explain this in way more detail. But obviously we should be considering the cost of the algorithm, whether it's the most efficient method we can use. Is there other more appropriate methods that can be put in place? And a way we can count that up is by considering the fundamental operators. When is arithmetic happening? When is comparison happening? When is assignment happening? How often are these things happening? And are they within a loop, which would then cause even greater repetition? Because what we want to be able to do is make sure that that algorithm will work in any data size and will be appropriate to be used. When we're writing algorithms, we wanted to write in pseudocode. There is a style for code in OCR. These in the spec, I'll include a link to this so that you can sort of see it. But that ultimately we need that and be aware of that for the exam questions in the way that they're written. What isn't required though is for you to actually learn that to then write in it. So the pseudocode we can actually write can be simple bullet points, flowcharts, as long as it's clear that there is logic at play and what that logic is, and that anybody could read it and understand it, or certainly a programmer could read it and understand it, well then that is suitable. The closer you can make that to look like programming code, Obviously, that means it's more efficiently written, it's perhaps more suitably written, but that's an end point, really. We don't need to get there first. We're much better to get the logic correct in the right order and then think about whether we can reduce the way we've explained it, and is there sort of other things we can bring in, such as using, say, a mathematical symbol to replace, writing the sentence out, add this to this one, just making it more efficient as we go through. Again, like I said, relax on this. I've seen so many students worrying about this, that I can't write like that, I don't understand how, etc. And don't fall into the trap of thinking you're having to write Python or you're having to write JavaScript or something. You're not required to do that. This is purely an explanation of the logic that you're applying to solve a problem, and you're just trying to make that as easy to read and understand as you can. And obviously, the more efficient we can make that, and the more similar to code we can make that, obviously that's the better, because that makes it easier then to transfer it in to another language such as JavaScript or Python. Remember, what we're not required to do is copy and paste the pseudocode, put it into something like Visual Studio and click run and expect it to work. We are not writing code. We are writing a version of code that helps us to consider an algorithm and to think about how it's going to work. Like I said, the process of this, what I would always encourage you to do this is write out in full English the statements that you intend to, the sort of process, as much just to get it clear in your own mind, to make it clear for you to see what's going on. Then start to replace as many different things as you can with logical operators, the use of the word and, or using mathematical symbols, again, to represent things. And ultimately, what you're just trying to do is reduce down the quantity of actual language that's there, make it as quick to read as possible. And then, if it's appropriate, bring in things like loops, put things into subroutines, separate things up as and when it's appropriate. But that's very much obviously down to the situation that's at hand. We can use this to make sort of comparisons, and therefore going to give you an example of some pseudocode that you can sort of look at. So here we're taking two numbers, we're comparing it with each other. We've then considered if the number is the same, we're going to have an output saying they're the same number. And if the numbers aren't the same, well, then we're saying, no, they're different. What we want to do then is take that quite wordy way of writing it and then translate it into pseudocode. And as you can see here, I've got a simple example of that. You can see that in the box there, it looks like sort of like a bit like Python code. It looks a little bit like you'd expect a programming language to look. And that we've used and exploited little tricks of programming languages. For example, the order of the statements. So the A being the variable, and then the first number being the input that goes into that variable. The symbol of the equals assigns it to the variable of A. In the third line down, we've used an if statement. Ifs will have an else with them, so therefore it makes a natural case to do that. And again, the use of indentation shows that the print is within the statement for the if. Again, the two equal signs there is a way of saying as is the same as. So we're just making it easy to understand. The actual print statement there is actually Python, isn't it? Actually, the way that Python would do a print to its terminal. So it's just using the same thing. And again, if that's comfortable for you to do so, that's fine. What you should be careful of, that you aren't just writing Python here, though. That's not what's required, and therefore just be mindful of that. Because again, the idea is that a programmer can understand the logic, and then they use their knowledge of C++ or whatever it would be to then translate your logic into the syntax that they require for their language. Well, thank you for watching. I really hope you found that useful. It really does help me to help others if you like and subscribe, so I would really appreciate if you do that. And obviously, if you've got any questions about anything, just put a comment below. Thanks a lot. Bye.